And now the examples at last. So here I chose a few examples for you because I think they're particularly interesting after what you have already seen in the previous lectures. So this has the usual structure, is like example. This is the examples about ring LM1, which is a first introduction to the polynomials. You already know everything about this, but you will see maybe some operations we haven't met yet. So here is program, and you know, when there is program, put your code there. So the interesting code, the main code is inside this function. So what does this example do? It shows how to create one element. Before creating the elements, you need to create the ring. You already know this. And then you can print out the ring element, the polynomial, in this way. You can multiply the polynomial by 2 and add 3, and you get this. You can compute the square. You cannot use in C++ this for making powers. In principle, if you know C++ well enough, you know that we might override this the same way that we defined times and plus. But the problem is that in C, the priorities on the operations are not what you expect. And so it would be really dangerous to override that to mean the powers. So that's why we are stuck for writing powers like that. And what other informations do we get out of it? We get out the owner of F, which is in COCOA 5 is ring of F. And then it says if this owner is a polynomial ring, which it is in our case, then it prints something like this is an element of a polynomial ring, these are the indeterminates, this is the coefficient ring. So we compile it. Actually, we compile everything. We compile everything, and it should be that everything is already compiled, actually. But not everything. Okay, I stop it. I thought they were. This surely is. So I can write, just to make sure, make X ring element LM1. This is already compiled. X minus ring LM1. So when we run it, it prints what we saw it should print. So it prints the value of F multiplied by 2 plus 3, and the square of F. And then it checks the ring, the owner of F, which is this ring with the ID number 2, and it is QQ of X, Y, Z. It is a polynomial ring, the indeterminates are X, Y, and Z. So I can extract the list of the indeterminates, and I can extract, as you see here, the list of indeterminates and the coefficient ring out of the ring of F. Okay, that was pretty simple. So let's see ring LM2. In ring LM2 is a bit more structured. So this is the program, and in the program it creates some rings. So it creates rings at Z and 2 elements, A and B, whose values is 5 and 7, and calls this test ring for ZZ, A and B. And then it does the same for other rings, like QQ creates A and B, 2 fractions, and calls all the tests. Then makes 2 polynomials, F and G, 2 polynomials, and call the test again. So what is this test? This test is a function which shows you things you can do. So it first of all, it creates one of the ring R, and then it prints out the two elements A and B, which are the two arguments, and then you will see you will evaluate the equality test, the multiplication, the sum, the inverse, the opposite, and the test if is 0, 1, minus 1, and computes the 10th power of the element. It checks if it is divisible, and if it is divisible, it computes the division. If the ring is a fraction field, it computes numerator, denominator, otherwise it prints that it cannot do that. If it is a true GCD domain, what does it mean? That mathematically we don't know if it is a GCD domain, a domain where the GCD is defined. If it is built as a GCD domain, like the polynomial ring, then it is a true GCD domain. If it is a true GCD domain, if there is a function computing the GCD implemented in CoCoALib. This is the definition of true GCD domain. So if it is a true GCD domain, we can compute the GCD. If it is a polynomial ring, we can compute a few things like the degree. If it is a sparse polynomial ring, we can compute the LPP, we can compute the weighted degree, and other things like LF and cut LF, which does something. At this point, instead of trying to understand really what it does and what it might do, we actually run it and see what happens, and then we go and see the code if we want to see what's inside. This is a structure that we do in our examples. X2 to have a function and create many environments and run this function on different inputs so that we compare the differences. I see. Here we have, this was an old piece of code, so it still had the Boolean to 0. I implemented it. Okay, sorry. I recompiled it. I added the line to print Booleans as true and false, which is more readable. And here it is. Okay, true and false. So now let's go at the beginning. This is long output. So you see the ring is at Z, the initial arguments are A and B. So I just look at the output and I see if from the output, if this example is interesting for me. So A and B equal are not equal, so they're different. The product is 35, the opposite of A is -5. A plus B means that it adds B to A, so A is modified and is now 12. And it does the operations we saw before, like is divisible is false, so cannot compute the division, is not a fraction field, so we cannot do numerator denominator, it is a true GCD domain because it's in ZZ, so we compute the GCD, which is 1. It is not a polynomial ring, it is not a sparse polynomial ring. Then we try with the rationals. We have two fractions, and again, that's something important that you need to know. You saw here we defined the fractions like that, which is a bit funny. There are other ways of writing it you can find in the manual. Because if we write in C 5 divided by 2, that's a division of integers. So it says 5 divided by 2 is 2 plus some remainder, so it's 2. It gives an integer. So we cannot write 5 divided by 2 in C. These are the operations, the comparisons, the operations on the numbers. Is divisible gives true because it's rational, so we can divide everything. That is not zero. And so this is the division, the result of the division. It is a fraction field, so the numerator is 29 of A. I can't remember what A was. 29 divided by 6, so the numerator is 29, the denominator is 6. That's right. I was a bit scared at the beginning. It is not a true GCD domain. It is one of those questions we asked yesterday. Can we do it or cannot we? Should we give an error? So if I asked if I can compute the GCD over the rationals, we can always return 1, but what's the point? I mean, we prefer to say it is not a true GCD domain, because if someone is asking for the GCD of 2 elements of a field, probably is not doing what is thinking is doing. So we return false. So we cannot compute the GCD in a field. It is not a polynomial ring. It is not a sparse polynomial ring. So the last example was the polynomial ring with 2 polynomials. They're different. This is the product, and so on, so on, so on, so on. The power is pretty big. Powers grow quite fast. Here is the power. A is not divisible by B. It is not a fractional field. It is a true GCD domain. I can compute the GCD of 2 polynomials, and it gives 1, as usual, often. And it is a polynomial ring, and so we can compute the standard degree. Standard degree is precise, means that it is a standard degree. DEG does the standard degree. So it's a degree 7. And then it is a sparse polynomial ring, so we can compute the LPP, the weighted degree. You see, it is in parentheses because the weighted degree in principle can have more components. So the weighted degree is a vector, is implemented as a vector. This is the leading form. It is the part of degree 7. And then catalef, oh, I can't remember what it does. So yes, it takes the Aleph, but it removes it from the polynomial. So now A used to be a longer polynomial. Now A doesn't have the part on degree 7 anymore. Okay, let's see another example. Which is polyring. Polyring 1. And here we have the same structure as before. So we have a function doing some computations in that polynomial ring. And we have many operations inside with the objects it is created inside, so that we can create many rings. And I show you it creates FF7. Maybe it is defined up here. Okay, FF7 is ZZ modulo 7. And QQ, we define it as ring QQ. So the first polynomial ring is F7 with symbols, the variable names. Remember, the symbols are the names, the strings. We can do whatever we want, almost whatever we want. So beta and psi with a capital or lowercase looks pretty horrible, but one might like to do that. Or we can have a symbol range, X, with indices from 1 to 3. We can decide the indices. There is no default starting from 0. So you have to specify the first and last index. And there is also something funny called new symbols, which is a way of making like anonymous symbols. So let's see it running. X ring, polyring 1, polyring 1. Okay, so you see, these are the 3 blocks of the computation. In the first case, we compute here, and we have all these operations. I'm not going to the details because you can read it out. You will see, I talked to you before, the default is the PP monoid OV with the order vector, because it is so essential when you do operations with polynomials to keep them sorted. And isomod, okay, I suppose that even here we don't have, sorry, the booleans, printed as booleans, so I can fix it. Okay, and I recompile it. Compiled. Okay, here it is. So the ordering, the default ordering is decreplex, like in COCOA 5. So the default grading is the standard grading. So it is homogeneous F. Where is F? F is here, and yes, it was not modified. Is homogeneous F true? Because it is 2 monomials of degree 1. We redo the same computations. Do you remember? This was the one with the indices in the indeterminates, and more or less it does the same thing. Here it shows you that the ordering is standard egg replex with 3 indeterminates. And this is the last example with the new symbols, which means that they are anonymous. They're useful in some funny occasions, especially if you have recursive calls creating rings. You want to be sure that you're not recreating the same symbols. This is a way. It looks horrible, but I mean, if you do computations and then map into a nice polynomial ring at the end, you will not see these funny names. And last, I want to show you something about matrices. Matrix 1. Because we haven't talked about them so much in CoCoALib. So it is tricky to write a matrix. It's much nicer to write it in COCOA 5. So we made a function that it takes a matrix from C, and I show you immediately what I mean with that. So I can create something like that, which is a vector of integers, machine integers. And then I can call my function that puts all the numbers inside a matrix in the ring R. Okay, so this is a bit dodgy, but usually you don't really create a matrix. You build up a matrix, and so that's why I'm showing you this example. So basic operations can compute the rank, the determinant, the inverse of a matrix, the adjoint of a matrix. And then there is another function that is an example for the matrix view type, which is a way of looking at the matrix. In particular, to explain better, I show you this. So if you have a matrix M and you take you take the transpose of it and you define it as a matrix view. This doesn't copy the matrix M. It just views M. So tr M is M seen as a transpose. So when I set some elements, some entry inside this matrix, I'm actually modifying M. So I must be careful when using matrix views. If I really want to create a new matrix, I must explicitly say that I want to create a new matrix from copying the matrix view. So I can create a matrix which is a copy of the transposed of M. And then there are generalizing this concept, I can make an identity matrix with a huge size, because what's the identity matrix is a matrix with ones on the diagonal and zeros otherwise. So this is the definition of the huge identity matrix. I don't need to create it. So the matrix is a function that returns me the values, and I compute the determinant of this matrix. I can do operations even with these huge objects. So we have here this huge identity matrix. Here we have a normal identity matrix, and then we can do these operations. You see, I create a new matrix with is the concatenation of the starting matrix and this identity matrix of size 4. This is interesting because you might want to create some matrices in this way, adding blocks of the matrix. So this instead adds concat vertically, so one on top and one below. And another matrix view is the submat. So I can take a submatrix, and again, this is a view of that submatrix. So if I modify something in this submatrix as a matrix view, I'm actually modifying the original matrix. And at last, block matrix 2 by 2 is a way of making a block of A, B, C, D, and creating a new matrix, a block matrix. So let's see it running. Let's see it running. Matrix 1. And here they are. Oh boy, this is very long. So this was my matrix 4 by 4, taken from the input from the DC vectors of integers. The rank is 4, the determinant is 3. This is the inverse of the matrix in Z modulo 11. And these are the other operations, the adjoint, and then we start again. Okay, here I don't have any nice separators. This is the matrix over the rationals. So the rank is 4 and the determinant is 25 this time, and compute the inverse. I can check it is really the inverse, multiplying by M. And then now we see something with the matrix view. So it says, see the documentation of matrix for the full list. So I told you we can concatenate horizontally. So we have the matrix M and the identity matrix. Then we added something vertically, and this is the output. And this, again, starting from this matrix, I see that I define the as the transposed, and then we modify the entry 1, 0, and indeed M now is modified with the entry 0, 1 being modified. And this is the submatrix, and again I substitute something in this submatrix with the first, with the row 1, 2, and column 1, 2. So is this one. So the entry 0, 1 is, now I'm getting confused, is set to 22. Submatrix 1, 2, 1, 2, 1, 2. I believe the 1, 2 means 1, 2. I should have checked this before. I was sure I checked. Okay. So 1, 2, 0 row, 1 column. That is strange. S, M, N. Okay. Now I'm confused. Maybe as the end. That's a awful way of ending this video because I am confused why this 22 is here instead of being there. Anyway, I will understand as soon as I finish this video. And this is the block matrix we get at the end. So this, we ran through some of the examples. So that gives you an idea of how to use the examples. So probably the best way is run the example, compile them all, run the examples, see if it does something that might be interesting for you, and then go inside, look at the code, copy the code, modify the code, and enjoy CoCoALib. Ciao.